Okay, welcome everyone for today's IMSC 60 colloquium. It's a great pleasure to have Debashish with us. So Debashish is currently a faculty member at Saha Institute of Nuclear Physics. So just to give an introduction, so Debashish did his PhD from TIFR Mumbai in 2011, lattice gauge theory. So he did very interesting works on solving the sign problem, and also on heavy quark diffusion coefficient, which is one of the most cited papers in the community. And as a recognition of his work, he was given the Rahul Basu Memorial Best Thesis Award. And then he moved on to University of Bern and later in Daisy Zoetan as postdoc members. And then he was an independent researcher at Dresden and Humboldt University at Berlin. And since his postdoc time, he has moved on to problems which are at the interface of gauge theories and condensed matter physics. So he has very nice papers on quantum link models and also on non-equilibrium dynamics in U1 problems. And he is currently now working on developing quantum algorithms on interesting problems in quantum field theories. And he will tell us more on that. So Debashish, please.
Hello. Yeah. So thanks a lot, Shanthan, for the very kind introduction. I apologize for this. Okay. Yeah. Okay. So thanks a lot, Shanthan, for the very kind introduction. And as Shanthan said, maybe he did not say fully, we were actually doing our PhD at the same time, and it was extremely nice to have Shanthan as someone to talk to and discuss with all the time. In fact, our first papers were written together, so it's been a great pleasure to have been discussing with him a long time. So also thanks a lot for inviting me to Math Science to be a part of your Diamond Jubilee celebrations, and it's a great honor to present a talk in this Diamond Jubilee Colloquium series. So today I will talk about how one can explore quantum electrodynamics and its cousins, right, using the methods of classical and quantum simulations, right. So the plan of the talk, the outline of the talk will be as follows. I will begin by reminding ourselves about the relevance of strongly interacting systems, so notably in gauge theories, that we come across from a wide range of energy scales, right? Starting from the very low energy scales that we typically encounter in the context of condensed matter physics to the very high energy scales that we encounter in the context of high energy particle physics, right? Having said that, I'll then go on to describe a particular class of models within this paradigm, within a new paradigm of QFT, right? Sometimes called D theory qubit regularization, and these class of models, which are called quantum link models, right? They have the potential to describe all these various phenomena that occur from condensed matter to particle physics under one umbrella, right? So essentially, you have a class of models. You can choose various things to describe the effective physics that you're interested in. And we'll see certain examples of how familiar physics we know about emerge from these theories. So not only those, I will then give examples, some novel physics scenarios that can be understood much better using the language of quantum link models, particularly when you want to bridge the gap between particle physics and condensed matter physics. That's one of the main successes of these models, I would think. Finally, I would conclude by giving you an outlook about where we stand with these prospects of quantum computation and how we can push these ideas in the next few years to 5 years to a decade, right? So let us begin with the formal talk. So for many of us, right, our first acquaintance with a theory that explains the real going-ons in nature, right, it happens when we learn the theory of how light and matter interact with each other, right? As you all know, the microscopic theory in this context is known as quantum electrodynamics. And quantum electrodynamics describes how when you have two electrically charged particles, when they interact with each other, they exchange photons, right? And accordingly, they are going to scatter or interact and so on. Now these photons, they also have a real existence to the extent that if you take a very strong beam of radiation and you shine it on a material, then depending upon, in certain circumstances, you can excite an electron from the surface, or you can excite a photon of another frequency. And even more, these photons can actually interact among themselves in the presence of matter, right? That's important. And this is sometimes called this Delbruck scattering, right? So now we are in a stage where we can say with reasonable confidence that we understand how light and matter interactions work, right? However, this was not the case, let's say 50 or 100 years back, right? So the stage that we are in actually was started, the entire formulation of a successful theory of light-matter interactions actually started long back in the early years of the last century from the works of Einstein, Planck, then Niels Bohr, and of course in the entire period of the 20s and the 30s, this was pushed by works of Dirac, Pauli, Schrödinger, and so on, until in the mid 40s and 50s, Schwinger, Tomonaga, and Feynman really formulated quantum electrodynamics in the way we understand it, right? However, the ramifications of the theory, right, were still not clear, I think, at that point of time, and many applications subsequently have been made on this to understand other interactions which affect, for example, theories of condensed matter physics. And as you can see, there have been so many Nobel Prizes on the way to mark various developments that has happened. And it has not only helped in understanding of basic physics, but as you all know, this has changed technology to a great degree, right? So a key message is that, of course, it takes time for things to be well understood in a way, when we can confidently say we understand it, right? Now, around the later part of last century, right, another of the cousins of quantum electrodynamics was making its appearance, right? And this is literally a strong cousin of quantum electrodynamics, right? This is called quantum chromodynamics, and this theory describes the interactions, the physics of the strong interaction. And this theory is literally a strong cousin of electrodynamics, in the sense that unlike electrons and photons, which interact, perturbatively or interact weakly, this theory is strongly interacting. This theory, to the extent that the particles or the degrees of freedom that this theory deals with, these are the quarks and the gluons, and then they carry a color charge, right? So this is the name chromodynamics, right? The dynamics of the charge, the color charge, and these quarks and gluons interact with each other very strongly, to the extent that they are literally permanently confined within other particles, right? And these particles are the protons and the neutrons, and often collectively we call them as hadrons, right? So it was not easy to study quantum electrodynamics, right? Especially at low energy scales, in the scales that we see around us, where matter is made of protons. However, when you postulate the existence of quarks and gluons, right? Because you could not apply perturbation theory. So the method that was extremely successful in QED could not be applied here, right? So it was only in the 70s, right, when Ken Wilson actually pioneered how you can non-perturbatively study the theory, right? So it's only since then we started understanding how the theory works. So Ken Wilson did this by taking this theory and non-perturbatively formulating it on a discrete space-time lattice, and he used. So not only that, not only did he formulate it, he also used non-perturbative Monte Carlo simulations to compute, right, physical quantities such as the masses of the particles that we see around us, right? And this method, which started off, let's say, in the early to mid 70s, has actually been pushed to an extreme state of sophistication, to the extent that you see this plot here. Now, this plot here is already about 20 years old. What this plot is telling you is that if you take certain inputs, right, and in this case the inputs being the mass of the kaon, the pion, and this cascade, the sigma, you can actually, using ab initio methods, right, compute the spectrum of all the other strongly interacting particles, right? So you have the rho, the k star, then the various nucleons, the lambda, and the higher resonances, right? So here you see the experiments. So these are the experimental lines and the widths of the resonances, and these red dots with error bars are the predictions or the results that we get from lattice QCD. So it really establishes lattice QCD on a very firm pedestal as a way to non-perturbatively, compute the physics that we see around us, right? And not only that, in fact, lattice QCD tells us a lot about when to expect, perturbation theory to work. So of course, this calculation that you see here is a calculation of the strong coupling constant alpha s, right, as a function of the scale mu. So this is what happens in quantum field theory. The couplings that we write down, they acquire a dependence on the energy scale, right? And you see that at very low energy scales, which correspond to energies that we see around us, the coupling is extremely strong, so therefore invalidating perturbation theory or weak coupling methods. But as you go to very high energies, you can still apply perturbation theory, right, as was used to understand the partonic structure in the 70s. And now, not only that, so lattice QCD actually goes a few steps further. It says that if you take this matter around us and you heat it up to very high temperatures, right, of the order of 10 to the power 12 Kelvin, you give rise to a new state of matter. So that's the quark gluon plasma, a state in which these color degrees of freedom are no longer confined within these baryons or the mesons, but they spread across on the medium, right? So that's when that's where the medium property, the color becomes a property of the medium. And of course, Shayantan is an expert in this physics. Now, so we've talked a bit about high energy gauge theories in high energy physics. It turns out that gauge theories also have an equally interesting role to play in the low energy side, right, especially in the context of condensed matter physics. So an example there is in fact, a pedagogical example there is the physics of frustrated magnets. So frustrated magnets this is a class of condensed matter systems in which the quantum mechanical degrees of freedom, and in case these degrees of freedom carry spin, right, they cannot relax to their lowest energy state because they experience repulsions from their neighbors because of their placement in a crystal, right? So some examples that we'll consider or are relevant to us is that a water ice. So this is one of the 11 phases of ice that, the naturally occurring water ice that occur. Or a more extreme example is the spin ice. So this is some holmium titanium oxide, right? So in these materials, what happens is that the unit cells, right, they are arranged as corner sharing tetrahedra, right? And what you should think about is that there are these atoms which are sitting at the corners of the tetrahedra, and then there are other atoms which are sitting at the center of the tetrahedra, just as you have here, right? Now, due to either covalent or ionic bonding, what happens is that a dipole moment is created between the centers of the positive charge and the negative charge. And these dipole moments are created in such a way that if you were to describe one single cell, right, one single tetrahedra, one single unit cell, you would have to use an antiferromagnetic coupling between the spins, right? So you would have a J times SI dot Sj, where J is positive. And now, if you only wanted to look at the physics of this single tetrahedra, right, you can easily convince yourself that there is not one single ground state, but rather 6 ground states that are possible. And this corresponds to 2 of these dipole moments pointing in one direction and the other 2 pointing in the other direction. And these states are, called ice states, right? Because, they were first identified in water ice. Now, as a next step, if you want to consider this entire crystal as a unit, right? You want to think of this as a many-body quantum system, which is the condensed matter way of doing quantum field theory, right? Then you would have to consider interactions, right, between these various tetrahedra. And there it turns out that you cannot, like unlike in a spin model where you can flip isolated spins, here you cannot do that. And of course you can do that, but if you for example flip one isolated spin, right, I'm really talking of dipole moments, which I call as spin. Okay? So if you do that, then your system goes into an extremely high energy state, because it ends up violating certain constraints that are favored. The only natural way of doing it is actually to flip 2 spins belonging to each tetrahedra. So the minimal possible thing you can do is, as shown in this example, is that you have 3 different tetrahedra, see 1, 2 and 3, and in which in each of these tetrahedra you end up flipping 2 of the spins, right? So you see something that was moving more or less in this clockwise fashion has actually shifted to the anti-clockwise fashion with 2 spins belonging to each tetrahedra. So this is what is called a loop operator, right? And these loop operators are exactly the hallmark of a gauge theory when you write it in the Hamiltonian formulation, right? So therefore, it's not a surprise that the low energy spin liquid admits a gauge theory description. But one thing I wanted to emphasize is that notice that the energy scale at which this happens is like 100 millikelvin, right? So this is like 10 to the power minus 10 MeV. On the other hand, if you remember the energy scales we were talking about before, this is almost like thousands of MeVs. So the main point I want to bring out to this example is that no matter at which energy scales you are looking or you try to understand the physics of, gauge theories do provide a very useful mathematical way of writing a microscopic theory from which you can extract the phenomenology of using an ab initio methods. So all these statements would lead you to think that we have been reasonably successful in dealing with some aspects of these strongly interacting theories, right? But how did we do that? So, so these first principle solutions, at least broadly can be classified, the success of this can be attributed to several different independent factors, and one of this was this non-perturbative definition on the lattice. But not only just the definition, but there was a lot of input, right, which was also done to develop the theory in terms of constructing the renormalization properties of operators that you write down, how to treat the lattice discretization effect, how to take the continuum limit, and so on, right? But theory was also not just the only thing you needed. You also needed to develop very efficient numerical algorithms, right, in order to run these systems on or large-scale Monte Carlo algorithms on computers, right? And this was, of course, the third thing. You need the extremely fast and extremely reliable high-performance supercomputing in order to get to some interesting physics, right, that we see around us. However, in spite of all these advances and the state we are in, there are certain very crucial areas which we would like to understand, but we cannot make progress, right? So, but again, perhaps this is already known to you, but let me just refresh. So one of the things is the equation of state of dense systems, right? Especially what happens inside neutron stars. Now we know that the microscopic theory should be or is quantum electrodynamics, quantum chromodynamics, excuse me, at very high baryon densities, right? When you pack matter in a small volume at very high densities, you give rise to the very dense phases of matter which are expected to occur inside the cores of neutron stars. However, the method that works so well at zero to compute the masses of the particles cannot help us. Another thing we want to understand is this non-equilibrium behavior of strongly interacting systems when you collide them. So when the study of quark gluon plasma, right, one of the things we do is that we take these heavy ions, we collide them, right, at very high energies, and so of course quark gluon plasma is expected to form after the thing has equilibrated. So we need to understand, right, from first principles how the matter that is formed after the collision can equilibrate, right, to form the equilibrium quark gluon plasma that is predicted by the lattice. So this is something that we want to understand, but at the moment we can only do with very effective field theories and some models. Well, in the context of condensed matter physics, there are some very famous examples of frustrated magnets or high temperature superconductors that we also want to study, but we cannot study them with the conventional tools that we have, right? So why is it? So what stops Monte Carlo from working in certain regimes, whereas in other regimes it seems to work so well, right? So so this is perhaps a very it's a slide only aimed at the students. So this is exactly a very brief introduction to what Monte Carlo would do, right? Or how it tries to compute things. So it's essentially a probabilistic way of computing certain functions. So if you wanted to compute this area of a circle, right, then you would just take some random numbers within some this -1 to +1, and you would just assign 1 or 0 depending upon this if this is within the circle or not, and accordingly you would compute the sum. Right? And what happens is that as you take more and more numbers, right, more and more n, you will see this value qn, right, it would approach this exact value pi. So the deviation, in fact, so what is important in Monte Carlo is that the method of Monte Carlo not only gives you a mean, right, the estimator of the mean, which approaches the correct value, but it tells you how fast it approaches the correct value. In other words, it can predict the error, right? So if you compute the error, right, which is delta q, this is just expectation of w squared minus w expectation whole squared, take a square root, and you look at this quantity which we call a signal to noise ratio, you will see that it approaches the exact value with a polynomial scaling, right, 1 by square root n. So this is the important part. If you need to make your answer precise by a factor of 2, you should take 4 times as many measurements, right? So, so using this method of Monte Carlo, right, you could do various things. You could compute, for example, the area under this curve. Again, you can compute the value of square root pi. This is a simple example. And here you will see that uniform sampling does not help. You need to sample in such a way that you are sampling the parts of the distribution which are non-zero, right, rather than 0. So this is another crucial thing to keep in Monte Carlo methods, that you should be careful in your sampling. If you're not careful in your sampling, you can just not be successful. Now the third example is a case where it's a disaster for Monte Carlo. Why is this so? So in this case, you see we just have the same Gaussian, but we have modulated the Gaussian with an oscillatory term, right, a cosine of kx term. And now what happens is that instead of the first 2 cases where the value of the function was always positive, right? So this function e to the power minus of x squared was positive. Previously you had a, previously this was also positive. This was also positive. But now this particular function is not necessarily positive because of the cosine factor. So this means that many of the actual measurements that you get out of your of your algorithm, they are going to cancel each other out, right? And they're going to give you a huge error. In fact, you can quantify your effort needed. You know the exact value of this integral. This is simply square root of pi times exponential of minus k squared by 4, right? Where k is 12 in this case, right? And now if you want to compute the signal to noise ratio, which we showed was polynomial in the last slide, here you see that this number is exponential, right? Exponential of c times k squared. So this means that in order to have an error estimate which goes down and which you can trust, you need exponentially as many signals, right? And this solution or this is a problem that plagues Monte Carlo calculations in many cases, and this is called the sign problem, right? Where the polynomial scaling that you've had in certain regimes, they actually change to non-polynomial scalings, and then you're completely lost, right? So this is the case that happens at finite density. This is the case that happens at real time, and we lose the efficacy of Monte Carlo so much. Now, so how does one make progress, right? So one of the directions that has been in vogue ever since Feynman said this in the 80s is that is 82 in fact. So he says he's not happy with the classical theory, because he says that nature isn't classical, and actually if we want to make a good simulation of nature, we should make it quantum, and it's a wonderful problem because it doesn't look so easy. So clearly he didn't, I mean, Feynman being Feynman, he still was trying to struggle with how to do this quantum simulator into a, quantum simulations into a field which would compete with the classical methods, right? And that's also the thing that we are doing, right? So yes, so if you have questions, you can ask me anytime. I'm just going to change gears and become a bit more specific now on, right? So So it turns out that if we typically take the quantum field theory models that we've learned so far, right, we learn in our QFT1 and QFT2, and if we try to do quantum simulations with those, you can do them of course, but there are lots of conceptual and technical challenges that come up, right? So one of the obvious problems is that, for example, if you take a scalar field theory, right? Now you know that the scalar field theory, even a free scalar field theory, right, is composed of many harmonic oscillators, and even the Hilbert space, in the Fock space that you would try to write down for a scalar field theory would be infinite dimensional, right? So clearly these quantum simulators that are coming up, they tend to describe, or they can effectively describe systems with a finite number of Hilbert spaces. So how do you deal with that? You would have to put a cutoff. You have to put a truncation on the amount of states that you can actually deal with in conventional quantum field theories, right? So that's one of the problems. So in fact, so exactly because of this and some other reasons, which I'll not go into, it's useful to consider an entire class of other models, right? And the idea we use to look at other models actually is inspired by renormalization group, in the sense that if you are expecting to describe a phenomena that happens in low energy physics, you should take a model that has the right dimensionality and the right symmetries, right? So this is a model that has been, this way of thinking has been successful a lot. So one can easily think of the successes of the chiral perturbation theory, right? Chiral perturbation theory is not QCD, but chiral perturbation theory has had remarkable successes in describing the low energy scatterings of mesons, right? So as long as you are keeping the quantum numbers and the dimensionality correct, you should be getting the right physics. So in that, armed with this insight, we actually look at a class of generalized lattice gauge theories, right? Generalized simply because they extend the class of lattice gauge theories that was originally proposed by Wilson, and in fact they have been studied both in the context of particle physics as well as the condensed matter physics. So these people whose names are in blue, they were mostly working from the particle physics point of view, whereas these people whose names are in red, right, they've been working on these models from the condensed matter point of view. So what these models do, as I'll show you, is that they realize continuous gauge symmetries, right? That's exactly what we want to keep, because QED and QCD both have continuous gauge symmetries. However, they realize these gauge symmetries using discrete degrees of freedom and with finite dimensional Hilbert space, right? This is the key word, the finite dimensional Hilbert space. And this is exactly what we will see, this thing. So therefore it extends the Wilson formulation of gauge theory. So Wilson formulation normally has an infinite dimensional Hilbert space, as I'll also explain in a moment. But not only that, these class of models also offer the possibility of new physics scenarios, right? This I'll also hope to give you some examples of. And moreover, because they have a finite set of states, you can easily map them onto the state space of quantum simulators, right? So this is one of the advantages for using them. You can really implement them in quantum computers. But even for us theorists, right? So of course, this is a job for experimentalists who will implement them actually in experiments. But also for theorists, this is also a very exciting game, because we can develop many of the techniques that we know. So for example, many of the effective field theories, right, to deal with these models. But also many numerical methods can be developed, right? Such as Monte Carlo methods, tensor network methods, and the development of these numerical methods, of course, will positively impact even the current numerical simulations of QCD, right? That's at least the hope that we all have. So how do these models work, right? So let's take the very simple case of lattice QED in 1 + 1 dimension, right? So when I talk about lattice QED, I still mean Wilson's formulation of lattice QED in the way Wilson described it. So we'll have a one space dimension, right? That's the chain that you have over here, and the extra one is for time, right? So this is the Hamiltonian, which is going to describe time translations. Of course, I don't have the time here; it's just the space. So the Hamiltonian consists of a single component fermions, right? Psi and psi dagger. And these fermions can actually hop, right? So this can be annihilated at the site y and gets created in the site x. So you see an example like this. So it hops between the site 5 and the site 6. Now, the important part of gauge theories is that whenever fermions hop, right, they cause an associated change in the gauge field, right. This is, remember we are talking about the Hamiltonian formulation of the gauge theories. So we are thinking, so this means that whenever we are talking about Hamiltonian formulation, we should think of a basis at the back of our mind, right. The basis that we have is that of the fermion occupation. So whenever you see these circles, the fermions are sitting on these circles, the number density of fermions is, this is 1, this is 0, this is 1, this is 0, and so on. And in this case, there is nothing for the gauge field, so the gauge fields kind of exist in a state 0. So what are the gauge fields, right, before we proceed further? So in Wilson's formulation, the gauge fields, especially in this case, right, we're talking of QED. So we have a U1, right, U1 degrees of freedom. So the U1 degrees of freedom are the phases, right. So UXY, so this is the gauge degree of freedom, is represented by a phase, right, minus of I phi xy. And we have the canonically conjugate variable, right, which is the electric field operator EXY. So this is minus of I del del phi, right? Just as X and P are canonically conjugate, so U and E are canonically conjugate objects, right? So therefore, of course, just as the canonical commutation relationships you have between X and P, here you have those between E and U, right? So E and U give you a U, E and U dagger give you a minus of U dagger. Of course, in Wilson's theory, U is an unitary. U is this unitary operator. So U dagger of U is equal to 1. So therefore means that U and U dagger commute, right? So how do you obtain a Hilbert space representation of this operator? So remember, this is just a phase, right? And therefore it is nothing other than a quantum rotor when you think in terms of a quantum mechanical viewpoint. So you have a quantum mechanical degree of freedom that is moving on a circle, right? And you can then represent the various states as angular momentum states, right? So it can have 0 angular momentum, plus minus 1 angular momentum, plus minus 2 angular momentum, all the way to plus minus infinity. This is what we learn in quantum mechanics, and in fact this is just the electric flux of the system, right? So if the electric flux, so in this picture, then we'll be thinking about this electrical flux states, right? So when we have no arrows here, we simply mean that the electric flux is 0 in all these links. However, when we have an arrow like this, we will mean an electric flux of plus 1. Yeah. Yes. So U is a raising operator and U dagger is a lowering operator. So this U is the same. It's just I forgot to put XY in between. So the way you should think about them, we just said argue this is a quantum rotor eigenstate, right? Whenever you apply U, it's a raising operator. It's like the ladder operators, right? That's all. Psi and psi dagger are really creation and annihilation operators. So these are ladder operators, right? As you just pointed out, the state 0 then goes to 1, right? So if you act on 1, you will go to 2, act on 2, it goes to 3, and so on. And the Hilbert space is unbounded, right? So this is one of the problems of Wilson theory. You have to deal with infinite dimensional Hilbert spaces. Similarly, U dagger is a lowering operator, right? And of course, as I advertised before, this is a gauge theory, right? So what does gauge theory mean in terms of Hamiltonian formulation? This means that at every site, at every local site, right, you can write down this operator, which is nothing but a discrete formulation of the Gauss law, right? So notice that this is a divergence of E, right? So EXY is just the electric flux between sites X and Y, and EWX is the flux between W and X. So this is just the one-dimensional lattice divergence, right? And minus the rho of X, which is just the fermion density. So this is literally the one-dimensional Gauss law that I've written for you on the lattice, right? And you can show, this is a very easy check, that G of X commutes with this Hamiltonian, right? So you have an entire class of operators G of X at every site which commutes with the Hamiltonian, right? So which means that you can construct these unitary transformations, right? E to the power I Q of X theta of X times Gx. So Gx is the operator, right? It generates these transformations. Theta of X is a local variable between 0 and 2 pi, and under this transformation the Hamiltonian remains invariant, Right? So this is how the gauge symmetry is manifested in a Hamiltonian. And of course, like as in usual quantum mechanics, when you have so many operators that commute with the Hamiltonian, you have to choose, you have to specify the appropriate super selection sectors, right? And this we do in particle physics, for example, by saying that the Gauss law state has to annihilate. We'll only consider those states as physical on which the Gauss law acting on it annihilates the state. Right? This is how we think of it in particle physics. So if you're all with me on this way of defining quantum electrodynamics a la Wilson, we will now go forward and understand how quantum link models cause a difference, right? So again, we take the simplest possible quantum link model in 1 plus 1 dimensions, right? And also U1. And notice I have made the changes. So let me just probably quickly go back and tell you a bit. So this is, as we said, this term in the Hamiltonian was describing the hopping of the fermions. This is the non-trivial term. These are pretty easy. This is just the fermion mass. In fact, a staggered fermion mass. This is something we like in lattice QCD. Don't worry about it too much. You could also remove the minus 1 to the power x. Anyway, this is a fermion mass term, and this is a electric field energy term, right? This is the E squared term that you typically have. Of course, this is a theory in 1 plus 1 dimension, so you don't have any B squared, right? Now, when you talk about quantum link models, notice the changes that I've made, they are made in terms of red, right? So I've only changed the operators which relate to gauge fields. So U and E have been changed. The only difference is that instead of the Hilbert space of the quantum rotor, which was infinite dimensional, we now work with quantum links, right? So this is a finite dimensional gauge invariant. This works on finite dimensional gauge invariant representations. And in this particular case of a U1 lattice gauge theory, this finite dimensional representation can be chosen to be a quantum spin S, right? So whenever you work with quantum spins, you immediately know that for a spin S, you have 2s plus 1 degrees of freedom, right? That's the local degrees of freedom. And if you label, so of course when you talk about quantum spins again, you have 3 operators, right? Sx, Sy and Sz. And out of this, you can construct the raising operator, which is S plus. You have a lowering operator S minus, and the electric and the Sz operator, which I label with E, right? And interestingly, remember that when you make these labelings, right, you see that the commutation relationships remain unchanged. So E and U gives you a U, E and U dagger gives you a minus of U dagger. The only thing that changes is that U and U dagger no longer commute now, but gives you a 2 times E. However, now this is the most exciting part. This essentially has no bearing on the gauge symmetry, right? Because you go ahead and you compute again this commutator G of x times H, and notice that when you do the compute the commutator, now the Gauss law is written in terms of the quantum link operators, which is again the divergence of E, right? But now written as these capital E operators. You only need to use the commutations between E's and U's, because E and E commutes. So because you need to use only the commutations between E and U, which are not changed anyway, the gauge invariance of the final Hamiltonian remains intact. However, of course, you can point out that look, something has to be different, right? Because there is a new commutation relation which has come up, which was not there before. And yes, I will completely give it to you. This is different, and it's precisely because of this term that you can explore different physics, right, by choosing the representation of quantum spins, as I will show you, by choosing whether you have spin half or spin 1 or spin 3 halves, so on. You can actually decide the kind of physics you want to look at. And more interestingly, if you take the spin representations going to infinity, right, you will see that this particular commutator will vanish when you suitably scale the operators with S and you go back to the Wilson type theory. So this tells you an obvious way of going back to the Wilson type theory. Just take very large spin representations, right? So that is one controlling parameter, right? So a very quick, yeah. Yeah, it's exactly the same way. So you say, once again you say that the physical states, because you see the operator is the same, it's just only written in terms of, the form of the operator is the same. It just acts on a different Hilbert space, if you want to put it like that. So the structure of the theory remains unchanged, right? This is the important part. It's only the Hilbert space which gets changed. Previously we had a quantum rotor Hilbert space which we were working with. Now we have the Hilbert space of a quantum spin. And of course, when you think about it, it has to give you some different physics, and that's what it does. Only when you increase the spin representation so much that like the discrete states that quantum spins can take become continuous, that's one way to recover Wilson's theory. Yes. Yes, exactly. So this has the same, it has charge conjugation, it has parity, it would have time translation, so all these symmetries are there. So that's a very important point for us to go forward with this. Thanks for bringing this up. Sorry? Sorry, I didn't get it. So which one? Yeah. Yeah, you could do that. You could also do. Yeah. You could do that. I think you could in principle do that. Absolutely. I think there are some subgroups people try to make out of Zn theories from this, and yeah, that I think would fit in this. Absolutely. So just to familiarize you a bit with the notation, although I'm running quite late, let me just it's a very quick slide. So E is, we are talking about a basis which is diagonal in E, right? And I also told you that we can take different representations. So if I choose to take the spin half representation, these are the two values of E's I will get, right? Plus half and minus half. If I have raising and lowering operators for U, you know that U acting on the state is just going to annihilate it because it's already in the highest possible state. But a state which is minus half is get raised to plus half, and vice versa, right? When you work with the spin 1 representation, then there are 3 possible states that are allowed for us. You have +1, you have 0, and you have -1. And once again, you have these, the raising and the lowering operators. And again, as I just said, you can take S to infinity, and this will, you can analytically show in this case that you recover the Wilson's lattice gauge theory, right? This was shown quite some time back. And yeah, so there's another way of reaching the continuum limit that some of us, including me, think is more elegant, and that would be to do a D theory or a qubit regularization approach. But this I will not talk of, at least in this talk. Maybe if I have time later, I might mention this. So let us take a try to, now that you have seen quantum link model, let's try to understand one very physical example, right? So remember that Schwinger model, right, was one of the one of the reasons that Schwinger came up with this model was he wanted to show this phenomenon of confinement, right? So if you have quarks and this was expanded upon much more by Coleman later on, is that Schwinger model is a model that exhibits Quark trapping, I think is the exact phrase he called it. So if you allow us the imaginative license of thinking these psis and psi daggers to be quarks, right, even though they are single component fermions and do not carry color charges, Coleman was able to show that this is not Coleman this is just what Coleman, consequence, this is describing the phenomena. So Coleman was able to show that these quarks, right, these in the Schwinger or fermions in the Schwinger model, they were actually confined in the sense that if you pull them apart, you would give rise to an increasing, linearly increasing potential, right, just as one thinks happens in the case of QCD. So in this example, right, I have a quantum link model, but now in the spin S equal to 1 representation, right? So remember, in S equal to 1 representation, we are allowed to have these 3 states, 0, +1, and -1. And what we do in this case is that you start with the vacuum, right? This is just a vacuum state where you have, occupied empty sites, all the way through. So the Gauss law is satisfied everywhere, right? Everywhere in the bulk, but not in the boundaries because you don't have the right number of degrees of freedom at the boundaries. So that's why I've written this half and -half. What you can do now is that you can put an external charge anti-charge pair, right? You put you put a charge and an anti-charge pair here, charge and an anti-charge. I'm just thinking of this as quark and anti-quark. And because it's a U1 theory, right, it's just a single flux that can come out, not 3 fluxes as in QCD. So a flux line is going to come out of this Q, it's going to travel throughout the system, right, and it's going to end in this anti-charge. And moreover, notice that this configuration does satisfy the Gauss law because whatever flux comes in also goes out, right? So divergence of E is satisfied, in this state as much as in this state. Here, no flux was flowing through. Here, a unit flux was coming in and going out. So Gauss law is satisfied throughout the bulk, right? So this is an example of a string, right? We've just made a kind of a string, And what can happen is that, just as in QCD, right, we know that one of the models to understand QCD is that you have quarks which are confined. So if you pull up quarks, pull the quarks away, you give rise to a linearly increasing potential. However, in QCD, this confining string can break, right? And we know that this can happen because the string stores energy, and whenever the quarks can jump between one side to the other, the vacuum can essentially pair create a QQ bar pair, right? Whenever a meson forms, this string breaks, right? This exact phenomenon also happens in this model. So in this case, think of this state B as this string that goes from one end of the system to the other. Now, when the fermions are light enough, right, the fermions can hop. Now, in this case, hopping a fermion means that you have changed the vacuum occupation of the fermions, right? So this side, the occupation was 0, but it has a fermion now, so it has an extra Q. On this side, there was a fermion in the vacuum, but now it's no longer there, so it has an anti-Q, right? It's a Q bar. So therefore, this fermion hop has generated a QQ bar pair, right? Just in the vacuum. And of course, it has happened once, it can happen many times. And this gives the final state that you have a meson sitting at the end of the system, and you have the vacuum. You have the vacuum exactly as before. And in fact, you can make plots like this, right? Where I'm plotting the energy difference between having a QQ bar pair and the vacuum. So this is what is plotted on the y-axis, and in the x-axis, we are just asking, right? We install charges on the ends of the lattice system, and we ask what happens as you keep increasing the lattice size, right? So essentially, you're pulling them apart, right? And we do this for various values of the bare quark mass, right? See bare mass 0, 0.51, 1.52. So what I wanted to emphasize is that, see that the curve, for example, this blue curve, right, which corresponds to m equal to 0.5, this linearly rises for a very short time and then it flattens out. When it flattens, really, this means that you've reached the stage where the quarks, where the linearly confining string is already broken, right? Because at that point you are just pulling them apart. There are only mesons. They don't interact. They are no longer confined. However, if you have larger bare masses, right, like this mass m equal to 3, you will see that you will really need a long time before the string can break, and this is completely fits in with the idea that we know from in QCD, that for the QCD vacuum to do a pair creation, right, is much more difficult if the particles that need to be pair created are heavy, whereas this pair creation is very easy if the particles that can be pair created are very light, right? So the confining string, will persist for a much longer length in the case of heavier masses, right? So this is an example of a familiar physics that we've seen, and this is something that we already proposed quite some time back for a quantum simulator, and in fact this has been realized in some of the laboratories of the world. We'll probably come back to this a bit later. I just want to quickly emphasize that even using these models, right, we can do reasonably large scale numerics, because what I showed you till now was just a bare lattice model, right? So you can show that if you now do a set of extrapolations, right, where you increase the representation of the quantum spins, right? So you keep increasing S, right? So then you take the S tending to infinity limits, that would be the Wilson theory limit. Then you take the thermodynamic limit, right? You have a finite lattice, increase the lattice size, go to infinity, and finally you take the lattice spacing going to 0 limits, that is the continuum limit. You actually reach the correct, of course, some extrapolations are involved in this case, and effective field theory methods as well. So there is a good bit of analysis that goes in these calculations, but the final result is that we are able to actually go to the values. So these three, what are these three graphs? This is the lowest graph is the graph for the energy density of the vacuum, right? So this is omega 0. The omega 1 that you're looking at is the mass gap of the first excited state. In this case, this is the pseudo-scalar meson of the Schwinger model. In fact, this is exactly 1 by square root pi. And the second gap is the scalar meson. This is 2 by square root pi. So these are exact numbers, right, that were shown in results by bosonization by Coleman and other people. And you can see that you can reproduce these numbers, of course, within the errors of the system of these extrapolations. quite accurately, right? So therefore, you can achieve all the familiar physics we know using these models, right? But it's also possible to look at some more exotic physics. So one of the exotic physics that in gauge theories you are always interested in is when you have a topological, this theta angle, which is what we call. So this is one of the big mysteries in QCD. Why is a theta angle very slow, right? So that's one of the big problems. Of course, we are not answering that in any even close enough, but we can answer, we can realize a scenario of theta equal to pi in the Schwinger model. So so it turns out instead of the spin 1, right, that I was talking about, if you use spin halves as your degrees as the representation, right, then the spin half degrees of freedom actually allow you to represent the phase with theta equal to pi. And in fact, you can show, this is back to Shantan's question, with spin half, you can show that the symmetries of the system, notably the charge conjugation and the parity, are exactly the same as the Wilson's theory, as in Wilson theory with theta equal to pi, right? So C and P are exact at this point, but the dynamics of the theory can spontaneously break it. And in fact, this is what happens. So Coleman had studied this model at theta equal to pi and had shown that there would be a first order phase transition at between two phases at 0 m, and he had also predicted that as m becomes finite, at some point the first order phase transition would dissolve into a second order phase transition. Subsequently, people have studied these example extensively with in fact DMRG methods, right, density matrix renormalization group methods, and found out where exactly the phase transition can happen. And we also see with the spin half representation that there are two regimes, one in the regime in the left where the phase the symmetry is not broken and you have a mass gap. On the right hand side, the symmetry is spontaneously broken, so you have a phase which is coming down and being degenerate with the ground state, right? So of course, I mean, what I'm plotting in the y-axis is the gap, and in the x-axis is the bare mass, right, for a fixed lattice size. If I were to do the finite size scaling, which we have done, I'm not showing this, for different lattice sizes, you would see that the gap closes exponentially, which shows you that the symmetry is spontaneously broken on this side but not here. So this is the Z2 CP symmetry that I was talking about. And in fact, yeah. Right. So in this case, right, in this case the topology is only to the extent that you have a global charge conjugation and a parity symmetry that is spontaneously broken, right? So the theta term that appears in QCD is a much more structure to it than the term in Schwinger model, because Schwinger model is just a background electric field, what happens. So I don't think this will tell us anything about the theta in QCD. But all I'm trying to say is that this particular phenomena, if I want to study using the theta equal to pi, using lattice gauge theory's Wilson's method, it would be reasonably difficult because I would not be able to do simulations with it. I would run into the same kind of problems I was telling about, some of the sign problems. Yeah. Yeah. So. So in this model, we are essentially looking at the condensates that get created because as a result of the symmetry breaking, and this we are just trying to show that the same amount of physics comes up with the quantum link models. So we are not addressing that exact topological observables. We just no, theta is a continuous variable, but theta is set to pi. It is not changed. It is just changed. It is fixed at pi, and at pi we are just changing the bare parameter mass. And what Coleman also had predicted that for certain values of mass, the symmetry is spontaneously broken, but as you change in mass, the symmetry gets restored. And this is a second order phase transition in the Ising universality class, which is exactly what one confirms, or in the static calculations, right? But then just to take this story a bit further, maybe we can come back to the question on topology later on, is that so this particular behavior, right, actually exposes some very interesting dynamical physics that are present. So if you start from one of the ground states, right, where CP is spontaneously broken, and you put the parameter in a Hamiltonian such that the Hamiltonian favors the CP unbroken ground state, right, then you will see very coherent long range oscillations that come about. And notice the x-axis, right? I'm talking about tau, and tau is measured in units of 1 by t. And you'll see that these coherent oscillations go on up to like length scales of around 100 times the basic energy scale of the Hamiltonian, right? So these things happen, and in fact, this was also realized in an experiment. So there is a lot of story behind. So this itself forms a material for an entire talk, which I will not have time to go to. But it turned out there was an experiment on a cold atom, on this Rydberg atom system, performed by the group, a group in Harvard, right? And then they started with this model. Not with this model. There is also another interesting thing. They started with a model which is called the PXP model. And this model is rather famous in the context of condensed matter physics, right? So this model is again a constrained model, and this model tells you that you can have spins in whichever ways you want, excepting that two up spins cannot be next to each other, right? And of course, there's a certain Hamiltonian of the spins, sigma x. So when they were doing this simulation, right, when they did this experiment with Rydberg atoms, they analyzed the results of this experiment purely from the PXP model, right? Then this was done in 2017, and some of our collaborators actually came up with a very interesting result that the model, this PXP model they were using, is maps on a one-to-one basis to the spin-half quantum link model that I just showed you, right? And this is exactly the content of this paper. So on the left-hand side, they have the actual results from the experiment. So they had some Rydberg atom chains, which shows this coherent oscillations, right? And on the right-hand side, they have the results from the quantum link model, which shows exactly the same kind of oscillations, right? Of course, the scales are different, right? Here, it's normalized between 0 and 1. This is normalized between minus 0.5 and 0.5. However, you see these exact oscillations persisting. And this led to a lot of studies in the literature about anomalous thermalization leading to quantum scars and so on. So this is really one of the new aspects in gauge theories regarding the dynamics that has come up, because experiments have become so easily available. And moreover, these models tend to show some very exciting physics, right? So in fact, let me just point out another experiment. So this experiment was done in 2020 by a group in Heidelberg, and what they were trying to check is that they were trying to study this Coleman's phase transition, right, at theta equal to pi, and they were trying to make sure that when they were, typically in these experimental setups, one of the big questions is the following: that of course you have a kind of a Bose-Hubbard model which you evolve in time, but gauge theories have the added difficulty that these things are constrained. These have constrained Hilbert spaces. So naturally, the question arises that when you are dealing with the Hamiltonian, where the gauge symmetry has to be implemented as an extra constraint, how well are you maintaining that constraint when you do the actual experiment, right? So that this is exactly what they were trying to do. So they were trying to look at some physical observables, right? As you go from as you do the quench from one phase to the other. On this panel, they actually looked at the violation of the gauge invariance, right? This is measured in epsilon, and you see that for most of the time, right, the gauge invariance is respected in better than 10%, right? Of course, all this is expected to improve as experimentalists get more and more control on their setups, thereby establishing this method probably as a more viable way of exploring physics in more involved theories. So I know that it's 5 o'clock. How much? 5. Okay, I'll try to wind up, right? So let me then just very briefly tell you, try to give you some flavor of the physics that we've been working on in higher dimensions. So this is a theory. Is again, it's U1 gauge theory, just to be very simple, in 2 space and 1 time, right? And what we have here is the basic element of the magnetic field that comes up, and this is the plaquette interaction, right? So as you know, you take the Wilson's lattice gauge theory. You have these U dagger terms, and if you were to naively take the continuum limit, this would give you a B squared term, right, which was absent in our previous discussions. Yet we are working in Hamiltonian formulation, however, and with spin halves, right? We should keep this in mind. So therefore, the Hamiltonian is just a J, this plaquette term, We could have added an E squared term for sure, but when you're working with spin half, E squared is a bit trivial. It's a constant. So that's why we've dropped it from the Hamiltonian. On the other hand, we've added this extra term lambda. Right? I'll tell you what this lambda is. What happens to the Gauss law though? So the Gauss law in this case, first of all, does not involve fermions because I'm only talking about pure gauge theories. Moreover, it involves 4 links now, right, touching a side because I'm talking of a square lattice. So if you are a particle physicist, you want to impose the particle physics gauge constraint, which is what we want 0 charges on the vertices, right? You will allow 6 configurations, right, as per Gauss law. However, if you are a condensed matter physicist and you want to study one of the theories that Anderson proposed of high temperature superconductors, this goes by the name of the quantum diamond model, then you have to stagger the system with charges +1 and -1. And there you have to consider, you know, these particular states. In fact, this is one of the models which very nicely interpolates between condensed matter and high energy physics. Let me see how much time I have to explain. In any case, just I should mention that remember the spin ice problem I was talking, those of you who are familiar with it, quite some time back. So if you take, so that of course is a 3-dimensional lattice, right? So if you squish the lattice on 2 dimensions, you will give rise to a checkerboard lattice, and this Hamiltonian is exactly the checkerboard Hamiltonian. So this is the Hamiltonian for spin ice, if you wish. Right, so what does this Hamiltonian do, right? The Hamiltonian has 2 terms. So first this J term, right? This J term wants to flip the plaquettes. That's what it wants to do. You see, this is the J term. It wants to flip plaquettes. If the plaquette is flippable like this, so these arrows signify, you know, around the clock flux, right? And it is round the clock flux is going on in the counterclockwise direction. So you will come and is J term, right? Is going to change the orientation and will become a clockwise oriented plaquette. Whereas this lambda term, so lambda term, if you want to go into detail, it's the square of the J term, but you know, subtracting all the difficulties, it's just a counting term. It just counts how many plaquettes are flippable, whether clockwise or anti-clockwise, it doesn't matter, right? So it's a counting term, right? So these are some examples of how the Hamiltonian acts on this. The J term, you know, I take a state which is all flippable, all plaquettes are flippable, right? It acts on it, it flips this plaquette but makes the rest of them non-flippable. That's what I mean by the shaded ones, right? And h of lambda just counts all the flippable plaquettes. There are 16 of them, so you get 16 times lambda. And in fact, this model breaks some lattice symmetry spontaneously, right? And so this is related to lattice translations and charge conjugations. And the best way to, you know, think about the physics is to think like this, right? There are 2 sublattices on the square lattice, A and B. And when your lambda is very large and negative, so when you are somewhere on this side of the line, so this is the lambda by J line, right? The electric fluxes order in such a way that all the plaquettes are flippable. Whereas if you decrease lambda, right, that's the time when J becomes more prominent. J just wants to flip the plaquettes. Then what happens is that only half of these plaquettes are flippable, which I denote by these shaded lines, right? So A is flippable, but B is not, right? So the A plaquette, the state on the A is just a resonating state with clockwise and anti-clockwise. So without going into any more detail, let me show you just one very interesting result, which is different, which is strikingly different from Wilson's theory, right? So Wilson's theory would tell you that this is a confining theory. You put whatever charges you want, right, in the theory as static charges. They are not, you know, they don't move in any way. You will see a confining flux tube, right, that comes out of the plus charges and will go in the minus charges. But there's only one flux tube. You can put charge +1, +2, +3 and whatnot. These charges will come, you know, come out from the source and go in the sink. In this particular model, right, these fluxes undergo a fractionalization. So it turns out that there's not one flux. So this is what are you looking at? You're looking at the energy density, right, of a 72 squared lattice. It's a 70, 71, 72, where I've put 2 static charges, right? So this is and you're looking at the energy density. Notice that these deep yellow ones are these static charges. They don't move at all, right? And then you have the flux tubes that are coming out from the charges, but there's not one single flux tube, right? There are 4 different flux tubes. and with a charge of +2, with some effective theory and analytic calculations, you can show that these flux tubes carry half integer fluxes. So the electric flux is quantized in units of 2. And these electric fluxes exist as continuous degrees of freedom, because these strings, right, these flux strings, they're not rigid strings, they can fluctuate. So the electric flux is really can be written as a continuous effective field theory. And then of course this model has some very interesting dynamical features. It gives rise to these so-called quantum scars. And I will not go in the interest of time, I will not talk about this, but all I'll say is that the presence of these excited states indicate that thermalization will be slow in these systems, right? And we've also explored these scars in a bunch of other systems, and this leads to a very interesting thought. If very simple theories such as these, right, show anomalous behaviors in dynamics and some exciting high energy states, it is not unlikely, right, that non-abelian gauge theories and QCDs could also have some interesting high energy physics hidden in these things, right? Of course, many of these things are under investigation, and yeah, I'll not comment further. So also I'm running out of time. So these models can also be studied on quantum computers, right? And sometimes these quantum computers are publicly available either by IBM Q or by IonQ. You just have to create an account, and you can simulate these plaquettes, right? At this moment, these qubits are still very noisy, so it's very difficult to implement very efficient interactions. But nevertheless, you get some answers, right? And these are actual answers from a quantum computer, by writing some circuits in Python, which is very simple to do. And by doing some reasonable error mitigation, you can see in cases where the quantum simulation works very well, it matches with the shaded lines which are theoretically computed. In other cases, it does not. It fails miserably, as you see. That's of course a big take-home message, that quantum computers are still very far, at least commercially available quantum computers are very far from doing anything very useful. This picture does tell you that. But then again, like quantum computers are improving, right? So so I think this is where I will stop. I hope I have convinced you that these quantum link models are indeed capable of they exhibit a class of rich phenomena in particle physics, and they have the potential of describing many situations in the context of particle physics, such as chiral symmetry breaking, dynamics of confinement, dense phases, and so on. I have not shown you an example of dense phases, but we have seen such an example. In the context of condensed matter physics, they can be applied to theories of frustrated magnetism and high temperature superconductors. And as we are seeing in the last couple of years, that these formulations have actually spurred on a class of algorithmic developments, right, and as well as quantum simulators of actually realizing these systems in the labs, right. So yeah, so I think at this point I'm just going to leave you with this figure with this graph that came up some days back. So we are usually used to see these Moore's law, right, in the transistor developments, where we saw that the classical computing power kept doubling every year, and that was one of the things in classical computers. So this is for quantum computers, only for one particular company by IBM Q. And actually they are showing how the quantum computing capabilities are evolving, and yeah, it shows an exponential, but be careful. These qubits are also very noisy, so it's very difficult to make anything very useful. But nevertheless, things are going to improve and things will get better. So yeah, with this I'm going to thank you for your attention, your questions, and your patience. Thank you.
Thank you very much for this very nice talk and questions.
Nice talk. So, so given that these quantum computers are noisy,
right?
So, do you have some particular simulation in mind which can take care of that noise? That this is within this noise limit and
yes,
can do the best job?
Yes, very good question. So let me just then go back to the slide that I had, which I didn't show. So right, so normally quantum simulators, right, they come with a certification level. They call this quantum volume, which means that, so in this case, if the quantum volume is 16, right? So quantum volume is defined as like this VQ is 2 to the power min times D and M, right? So what does this mean? So whenever you have a quantum circuit, right, you have certain qubits and you have certain number of gates. Right? This is what I mean. You have qubits, 4 qubits, and you're inducing an interaction between the qubits, right, by these various gates, right? So a quantum circuit, when you say, you know, the quantum volume is 2 to the power 4, this means that it can simulate noiselessly or correctly a maximal circuit of 2 units of qubit with 2 gates, so on. So of course, you know, most of the quantum volume is much too small to be actually used any practical purpose. So people have started to use some error mitigation techniques. And in fact, this is also is an example of that. So this uses on the notion that the system is actually an open quantum system, and if you increase the duration for which the quantum gates are applied, you will have more noise. So therefore, you can extrapolate behind, right? You can do a set of exposures in various times and then extrapolate back to the zero noise limit, which is what we show in these blue points. And for certain cases, we are able to beat the quantum volume and produce very good results like this. It matches with the theory lines. In other cases, we cannot. The system is far too noisy. So yeah.
Yeah. So I have a question regarding that scars you saw. So for the in the PXP case, so what we look for is like that. So there was a constant that the read board blockade. So we have a constant input space. So and there exists a Krylov subspace. Because of that there exist scars. So in your case, in the Swinger model, so what is the constant? And
So yeah.
and so is it like so what we look for is that the low energy subspace of the Hamiltonian, right? So in the condensed matter, so you are already in the high energy. So
Exactly.
what is the low energy for that
Right.
high energy?
Okay, yeah, very good. So let me just add one more thing. So the Schwinger model in 1 + 1 dimension, right, using the spin half, is exactly the same as the PXP model. So that's the first thing. So if you look at the entanglement entropy for the Schwinger model, you would also see this equally spaced scars. It's exactly the same model. This model that I'm talking about is the gauge theory in 2 spatial dimensions. Right? So therefore, it has a different structure of the excited energy states, and the scarring phenomena that happens, it's called a scar essentially because, why is it called a scar? Because normally what happens, right, when we think of quantum systems, the ground states have low entropy. The moment you go to very high states, right, high energy states, the so-called entanglement entropy starts growing. And here I have plotted this half chain von Neumann entanglement entropy as a function of the energy density, right, EL. So the ground states are really over here, right? So on the left hand side, you see that they are very less entangled as you expect them to be at very low energies, right? This is this. At high energies, however, normally states would have very high entanglement, as we know from various cases. In these particular cases, there exist anomalous states. It's back. Yeah. So in this case, we don't really understand, right, the low energy subspace of this high energy state, as you said. What I can tell you, what I can tell you though is that these states are simultaneous eigenstates of two non-commuting terms in the Hamiltonian, and that is why they.
So if you are supposed to look for this phenomenon in other models, so what things you look for, like? Yeah, so what is the thing you look for to look at the other models?
Right. So the other thing, so typically what we do is look at entanglement, right? This is supposed to be one of the diagnostic for diagnosing any atypical state. But then of course you can look for other quantities. And these other quantities being this So this is the local variable E, right? E is just the electric flux operator, and you're looking at the flux correlation function. And normally what happens is that these states all cluster about a single curve, and this curve is a prediction that you get from random matrix theory and eigenstate thermalization hypothesis. Right, which is supposed to explain how excited states behave, but you see these huge outliers, right? They are very far away from the ETH spectrum, or what is predicted by ETH, and if you look at some anomalous, if you see anomalies in such expectation values of local observables, you should try and identify them.
Yeah, so I'm also asking, like, if you are supposed to look for other models which can show this anomalous behavior. So what is the thing you look for?
So there is no one particular thing, right? Because so this thing is a bit like sign problem. Yeah. I think this entire field of scars is not that you know exactly why scars will happen. It's just that you have to be careful about the anomalous signatures that come up. So the first thing you should do is to look at that entanglement entropy thing. Right? So this is, in my experience, this is what has happened in at least our class of systems that we have seen. Right? In the second case, what we have done is that we've looked at this figure, which I never had a time to explain. This looks at the eigenfunction, right? This scar eigenstate. And this scar eigenstate, you see, has contributions from only a very, very few states. And this is very special, because if you typically take a very high energy excited state, it gets contribution from the entire Fock space. Right? But scar states do not, and that is one of the other criteria. Then you look at real-time dynamics. So you take all possible initial states, you do a real-time dynamics, and you will see that those states that have a large overlap with the scar, they will not thermalize. So this is the band which is indicated, this is the thermalization band. This is what, any typical state you start with would thermalize to in the very long time limit. But scars would not thermalize, they would come here. That's the second thing. The fourth thing, rather. Yeah. Right. Yeah.
Okay, in U1 gauge theory,
right.
Then there are strict results that because of infrared effects, the electron gets dressed by infinitely many photons, and its mass is indefinite, spin is indefinite, Lorentz group is broken, and is extraordinarily entangled states.
Yeah.
I don't see any of that here.
Yeah. So
I don't see, I don't know how to connect your results with quantum field theory.
Yeah.
At all, I should say.
A very good question. A very important point here is that when you are talking about quantum field theories like that, you really have degrees of freedom which are allowed to go to infinity.
That's apparently the reality. No?
Yeah. This is true. So in these models, remember, although they have exact U1 gauge invariance, right? I cannot. So first of all, I don't have any electrons in this model. I'm just talking about a pure gauge theory, right?
Yep. So there are similar results in pure gauge theory, where recently there have been results coming by people like Longo, that in fact, if you try to compute entropy of the quantum of the observables in some physical region, it is always infinite.
Yeah, exactly. So and it has to be, right? In some sense, when you're talking about quantum field theories, right? The quantum field theories have they have arbitrarily high excitations are possible. So in order to get any finite answers from them, unless we put some cutoff, we'll always get infinity. So that's my understanding. In these models, we have not taken the continuum limit. So if we were to take continuum limit, we could perhaps predict or at least show how does the infinity scale, right, in terms of the lattice spacing. Of course, I agree, it's going to go to infinite. So how fast to infinite will it go? Will it go as exponential with the lattice spacing or something else? We don't know the answer. It's a very valid question. I don't know the answer. I mean I'm aware of the question. Let's say.
Also, the limit of large n, the kind of quantum field theory you get by taking the limit of large n depends very much on how you want to take the limit.
Exactly.
It is already old results of von Neumann.
Yes.
So here it looks to be a naive activity. So compared to what has been done in the context of
Yeah. Okay. Okay. Yeah. Very good. So I think one of the reasons why this activity kind of makes sense is that so there are a couple of reasons. One of the reasons is that these systems, right, this entire phenomena that you see scars, right, you already have a many-body quantum system, and they're not small. They're big quantum systems, right, in the sense that if you look at the Hilbert space, there would be 10 to the power 8, 10 to the power 9 dimensional, really big with hundreds of quantum degrees of freedom, right. This would be something like your Hubbard model, for example, right. It's not at the limit of quantum field theories, but it's a reasonably big quantum many-body system. And you can compute these results, and in some cases, which in the second case of this quantum diamond model, we can even write down analytic results for thermodynamic large systems. And many of these results already contain surprises, right? Surprises as in you have two operators, right, which do not commute with each other, and yet we find eigenstates that are simultaneous eigenstates of both these operators. Right? So those results will not go away if you take the quantum field theory limit. It is just difficult, at least for me, to imagine how the physical scenario would look like in these results. And second of all, these atypical behavior that we see here can actually be put to use. So first of all, you can realize them in actual quantum simulators. Second of all, because these states do not mix with the rest of the ETH spectrum, you can protect quantum information. You can code these states to have particular information, and how you code it, we are not clear to that as moment. But if you can code certain quantum information there, then that quantum information will not be lost. So yeah, so this does not answer those questions of QFT, but it does show some promising. It does make some headway into identifying things.
Just one question. You said about the sign problem.
Right.
I thought the sign problem was that there was an I in the Euclidean formulation.
Yeah.
And not an oscillatory factor, but an actual I. You don't know what to do with it.
So it's not as simple as that, right? So one of the ways of saying that I is that, right, if I have an e to the power IHT, right, I cannot simulate it. That's one simple way of saying it, right? But sign problem is just, like a name we give. It's a technical name we give to various aspects of a signal to noise ratio. So one of this is, as you said, is e to the power I, right? There are other cases, for example, where the action, this e to the power minus s, is simply, a negative, or it oscillates between positive and negative. It's like for some configuration, it's not oscillating, not as in e to the power I. It's just like some configurations would have the Boltzmann weight to be, e to the power minus of beta is to be negative. And then we don't know how to interpret this as Boltzmann weight.
Yeah. Just one moment.
Yeah.
If S is not positive in exponential minus S, the functional integral diverges. Okay.
Yes.
So what? But I know that if you put a charged particle and couple it to electromagnetism, or take finite temperature theory, finite temperature you put a chemical potential, both give an I in the functional integral in the Euclidean formulation.
Yes.
So there nothing seems to diverge. It can exist quite nicely.
Yeah.
But you don't know how to calculate.
Point taken, yes.
S oscillates.
Yeah, but
that thing doesn't make any sense.
So we are not using the formulation of S, right? We are using the Hamiltonian formulation. We are not even going into writing an S. We have a Hamiltonian, we diagonalize the system, right? And we compute the systems from there. You're not even going to the Euclidean formulation. You're not even constructing the S. So that's a way around it.
So thanks for a very nice talk. So,
Thank you.
A few weeks back, I think Professor Shailesh Chandrasekharan gave a talk about a qubit regularization model.
Yes.
And the success to simulate the strongly interacting QCD. So here you showed that quantum links model is also very interesting and can simulate the prediction of strongly interacting QCD, right? So I was just wondering, is this they are kind of equivalent, or is it totally different, something like?
So they are equivalent.
Is
so
it?
it's just that, historically, the way this happened, So also, like this is like a nonlinear history, right? So people were considering these discrete, these finite dimensional Hilbert spaces already in various different contexts. So one of this was spin ice, as I said. People like Rockshire, Kivelson, maybe Anderson as well. And then on the other side, people and the particle physics community, people were considering what are called the quantum link models. So they are just the qubit regularized versions of, or at least one qubit regularized version of a gauge theory. So what Shailesh was saying was that there's a much more general class of models you can write down, not only for gauge theories, but also for scalar field theories. And there also, like as I started the talk by saying the bosonic field has an infinite dimensional Fock space, right? Because you could put in as many harmonic oscillators. So in the qubit regularization, you would not need to put an infinite dimensional Fock space, and yet recover the asymptotic freedom of the 2DO3 model, for example. That's the point.
Exactly, that's the point.
Yeah.
Okay, thanks.
Sure.
Any further questions? Okay, I just one question to you.
Sure.
So when you identify this gauge theories with this quantum links, or the spin systems, is there any direct one-to-one relation in the strong coupling limit, or is it true, or
So
is it true for any couplings?
So I think that the in the strong coupling limit there is a very clear relation, right? In the weak coupling limit, it's not so clear how the continuous gauge fields emerge from there, right? So it's also because as the more we work with it, the more it becomes clear that when you work with the quantum links, there are many parameters you can choose, and one thing being the dimensionality of the representation, essentially, whether I take a spin 1, spin half, and that seems to affect the continuum physics quite a bit. So that is, so these are, and these are essentially very non-perturbative questions, so that one cannot naively use perturbation theory to compute some of these. So that's why it takes a lot of time to understand, what would correspond to the fully, like in the simple cases that I showed, one has a good understanding about what representation to take, what couplings to use to get, to the string breaking or theta vacuum, these oscillations that I showed. But in other cases, it's not clear. So that's,
And also, when you take the largest limit to go to the continuum, but we know that in QED in 3+ dimension doesn't have a continuum limit.
So in that
this will not work.
This would just simply diverge. It would not have a meaningful in this case, it simply works because the theory is super renormalizable, and essentially a finite continuum limit exists. So as you said, in 3+1 it would not work, right? But we don't have the resources to check it.
So at some point, if you have a good quantum algorithm or this link model.
Tensor networks and so on.
Okay, so I see no further questions, so we can go for coffee and then thank the speaker again.
Thank you
We can
again
continue
for
our
your
discussion outside.